YouTube audience or those of you watching later. Any other questions about the administrative issues for the course? Or the material so far? To recap what we've seen, we started the course talking about prediction from expert advice, which is a very elegant and very simple model. Not easy, but elegant and simple, which I hope you will agree, very general. We showed how to extend it in various forms. The very general form of online convex optimization. We discussed efficient algorithms, online gradient descent, and then talked about mathematical optimization and better algorithms that are able to obtain better guarantees, better convergence, faster convergence, and so on. We talked about logarithmic regret with online gradient descent. And last lecture, we talked about online Newton step, which is a more sophisticated algorithm and has wonderful properties, especially for a family of functions that is also important in portfolio selection and various other applications that we will see later in the course. Today, I will talk about a different problem, which is called learning with partial information. And I wanted to start by describing the problem and then ask you for your thoughts. So suppose I have, let's consider the setting of prediction from expert advice. I am choosing between several different options. So I have maybe action 1, action 2, and so on up to action n. I don't know the outcome ahead of time. So me, the decision maker, has to choose an action. And after choosing, let's say I commit to action number 5 here. Then I get to see a reward or a loss for this particular action. And that's it. That's the only information that I get. In particular, I don't know what would have happened or what reward would I have obtained had I chosen a different action, different course of action. So this is a more challenging setting than the one we have considered thus far. When is such a model interesting? So for portfolio selection, this maybe is not very interesting, because if I choose to invest in some particular asset, I can open the newspaper the next day and I can see immediately the prices of all the entire market, and I know what happened in every single strategy that I would have picked. But in certain situations, this does make sense. For example, let's say that I route packets in an information network and I choose a particular path from source to destination. So in this setting, I route the packet and I can measure something called the round-trip delay. People here took networking, computer science, networking. I never took it, but I know there is such a thing, network round-trip delay. So that's what you can measure. And the point is that the packet goes through many different routers along the way, and they have some information, and they can calculate the time it took back and forth, or maybe even one way. But we don't know what would have happened had the router chosen a different path through the network. That we don't know. Any other ideas come to mind of applications of this setting? Kia?
Online advertising?
Oh, very good. Online advertising.
Because you don't know like how much people interact with that until you deploy.
Very good.
And you only know about that one ad.
Very good. So as someone who worked at Google for a long time, I should know that. So this is indeed the setting. Let's say you display ads on your, someone has a search query, and then there are various different ads that match the particular search. For example, I search for sports equipment for whatever my favorite sport is, swimming, and then maybe the search engine will choose to display some advertisement, and it can choose to display a car advertisement or a bathing suit advertisement or whatever. And there is only a limited number of advertisements it can display in the corner of the search results. And then we get to see whether the user clicked the advertisement or not. The search engine goal is to maximize something called the click-through rate, which means how many times people press the actual ad, and it means it's relevant, and that's how they get revenue. But let's say that we don't know what would have happened had we chosen different advertisement? Would the user click this advertisement, not click? We don't know what would have happened. Okay? So this is another example of partial information. Very good, Kia. That's a fantastic example. Any other application you guys can think of? Yes, Angelos? Traffic. So that's like routing, I would say.
Yeah.
Routing, yeah. Elijah?
Playing an adversarial game.
Like, you mean like chess or?
Yeah, we haven't gotten into sequential games, but you could think of something like chess where you somehow get a reward every action, and then
Right.
you don't know whether the action you take will,
Right.
like rock, paper, scissors,
Right.
in some sense.
Okay, so that's a good example. So game playing, this gets into the domain of reinforcement learning too, where our actions have an effect on the environment. They don't stand by themselves. So the state of the world changes after I take an action. That's not the model I'm describing now. Now I'm thinking of maybe rock, paper, scissors is fine. So rock, paper, scissors maybe is an okay example, but playing chess maybe is not a good example, because then I have a change of the board, and that kind of has more complications in the modeling. Here I have the same actions to take time after time after time. Yes?
I was just going to ask, like, let's say you take the same action over and over again. Is the outcome of, like, after each round independent of everything else he has?
Right, so that's a good question. So the model I'm thinking of, I didn't fully specify, is exactly like prediction from expert advice. So let me define it a bit more formally. This model I'm thinking of is called the adversarial or non-stochastic multi-arm bandit. And in this setting, we have a decision maker that chooses I from n available actions. Let's call it IT. Then there is a loss, LT of IT, which is a number between 0 and 1. And this is repeated again and again, and I measure. What do I measure? Well, I can try to be ambitious. So I can try to maybe minimize regret compared to the best action in hindsight, even though this is a strictly more difficult setting than the one we have seen before. So maybe I want to minimize regret, summation T, LT IT, minus minimum over all I star, summation T, LT I star. So to answer your question, I forget your name? Mayang. To answer Mayang's question, yes, the losses are chosen completely arbitrarily or adversarially and independently from one iteration to the next. And because of this adversarial nature that I hope you're now all familiar with and used to, we're trying to minimize regret compared to the best action in hindsight, because that's the only meaningful thing we can say. And the best action in hindsight is only determined in hindsight. It's not known in advance what it is, because the game has not yet unfolded and the losses are not yet determined. Yeah?
Sorry, how is this different from the, like, just the n-experts problem?
Okay, how is this different from the prediction from expert advice problem? Who can answer? Yes, Edouard?
We don't see the loss of
Correct.
each expert, but only the
Correct.
other.
So the difference is the information model. The information available to the decision maker is only one real number. Whereas what was different in the prediction from expert advice problem, we could have seen the losses of all experts. And we motivated that by the example that I myself gave, and Kaya gave, and various other people gave, of where this makes sense. This makes sense in many different settings. Another question here? Is the problem clear? It's clear that this is more difficult than prediction from expert advice? Is it clear? Well, it is indeed more difficult, but let's try to solve it. And the first thing we should try to reason about is what is even possible. Can someone try to reason about how would the lower bound look like in this setting? Yeah,
I have a question.
please.
Do we observe the loss after every step, or is it like at the end of the?
After every step. After every step. Otherwise, you can think about that setting as well, and you can reason about that this is basically almost nothing you can do. If you see it, all the losses at the very end. So every iteration, it's similar to prediction from expert advice. In prediction from expert advice, we would see the entire loss vector LT, which is in 0, 1 to the n, every iteration. And here we only see a real scalar number. Everything else is exactly the same. Yes?
Since we've only seen the loss for the action that we take,
Yeah.
like, how do we know about I star?
We don't. We don't necessarily. Yeah. Maybe we'll never know what I star is, right? That's an interesting point. Yeah.
I guess we can try and do better than our last approach, like in the last round, and that can be kind of our function for how we run minimus. Is like, as long as I do better than I did in the past round, I'm happy by some extent.
Yeah, that makes sense. Iterative improvement. We've looked at iterative improvement methods in this class. In fact, one can argue that every single algorithm we studied in schools is an iterative improvement algorithm in disguise. Whether it is the multiplicative weights algorithm or the gradient descent or Newton method or Cover's algorithm even, which is a form of multiplicative update rule. But notice that it's hard to argue about what is better than my last action if I only have seen one scalar of information. There are n possible actions. Think of n being a million. And I see one number. How am I supposed to make a decision in the next round? So that's why I started by asking you, can you reason about what are the limits of what we can even expect in this setting? What would be a lower bound on the regret? Can you give me a lower bound? Easy lower bound. I'm not asking for something sophisticated. Alex, what would you say?
Well, I was just thinking, like, since the loss is adversarial, can, like, they just choose that your loss is 1 every time and everything else is 0?
Okay, I like your question. So, we have to be precise here about how the game is played. The way that the game is played is that the player chooses an IT or a distribution over IT.
Yeah.
Then the adversary chooses a loss vector and reveals a scalar. Now, if I deterministically choose a point, yes, this can happen. Maybe the loss will be 1 for whatever I choose. And this also happened in the lower bounds for prediction from expert advice. We looked at the setting.
Yeah.
What happens for prediction from expert advice? Well, the adversary could have done that, but they would also destroy the best in hindsight. I should say very importantly that we allow randomness. How do we allow random algorithms? Just the same as we did until now. So the player is allowed to choose distribution over arms, over actions, and then the adversary can see the distribution but cannot see the outcome of the actual choice. So if IT comes from distribution PT, PT is visible to the adversary, but the actual IT chosen from it is not. Yeah. So, yeah, Elijah.
So for a lower bound,
Mhm.
this, I haven't figured out what exactly the value of the lower bound is, but maybe one way of approaching it would be to say, okay, the adversary is going to choose one action every round uniformly at random, and
Yeah.
it's going to assign 0 loss to that,
Uh-huh.
and then everything else is going to have a very large loss.
Okay.
And so then my intuition is that the decision maker, since like there's nothing to learn, since it's random, the best they can do is also sample something at random. And then they have a very high probability of getting a bad loss and a very low probability of getting a small loss.
I like this setting. Let's analyze it. This is a good example. I didn't plan on analyzing it, but it's actually a good thing to look at. So here's the setting Elijah is saying. Elijah is describing a situation where LT is equal to 1, 1, 1, 1. Then there is a 0 somewhere, and 1, 1, 1 everywhere else. So in this 0 is chosen uniformly at random. Now, if I, the decision maker, try to do something systematically, go over all possible experts and so on, then there's kind of a low chance I will hit the 0. So that's why I think you describe this example. It seems like a hard phenomena to discover, this needle in a haystack. So Elijah also suggests an algorithm. How about we pick IT also uniformly at random? So from these n experts. So let's analyze the expected regret of this algorithm. Can someone see what the expected bonus question? I think this should be possible. Can someone tell me what the expected regret of this algorithm on this particular choice of losses is? Yes. 1 by t. 1 over t, regret?
Yeah.
Average regret or total regret? You're probably talking about average regret.
Average.
Why?
I mean, if we are picking it up randomly, then like regret is just in the difference of the agent we pick and the best expert, and that is probably only different at the 0 point.
Angelos? It's a good direction.
1 minus 1 over n.
Well, are you talking about the expected loss?
Yeah.
I asked about the regret. Okay, the expected loss, okay, as Angelos was saying, the expected loss of the player, the expectation here is over both the choice of loss vector and the choice of expert is what? 1 minus 1 over n. Because the chance of the IT being exactly the 0 is 1 over n. What is expectation of LT I star? What is that? Also, right? So for every I, it doesn't really matter. I star, they're all equal. Okay? So then the expected regret is going to be 0. So this is an interesting example where it looks like a hard setting, but actually the expected regret here by a very trivial algorithm is going to be 0. Yes, question?
Should we not expect that, like for LT and I star, like we have n choices for which the I star could have been, like
Yeah.
perhaps one of them like did slightly better, but we get to choose them. Like shouldn't the expected loss be a little bit lower for LT and I star?
So this is a question this is a good point. So this is for any I star if I don't put the minimum inside of the expectation. What you're saying, I think what you're saying, and that will be correct, the expectation of the minimum
Yeah.
I star, and if I sum over all t from 1 to big T, LT I star, this is going to be how much?
Or I was just saying shouldn't it be less than 1 minus 1 over n?
By how much? That's true. This is true. It's going to be something like 1 minus 1 over n t minus something. Minus what? Can someone see? What? It's true what you said. Think of n as 2, let's say. Yeah. Yes. So it's going to be roughly something like square root t times maybe 1 over n. This is what's going to be here, which also indicates of the regret we will be shooting for. That this is correct. This is a good point. Yes.
Where did you get the square root t from?
It's the square root t. It's comes from. There is actually a homework question, I believe, in your current homework that describes it. So you can see your current homework and look. Did you do it already? So if you didn't, take a look. There is something very similar over there that's happening. So it comes from a random walk. So you have n random variables. Each of them has this expectation, but the variance behaves like n because you have 1 over n times t. That's how the variance behaves. So standard deviation is like root t. I'm not going to get into details. I didn't even plan on getting into this example. But it's a good example. It kind of shows you that even a seemingly hard setting, actually it's a very simple algorithm that solves it okay-ish. Maybe regret square root of t. Yeah.
this setting, can the adversary condition like what loss they choose to give based off of what the players, like for example, if they have like a distribution, you said earlier.
Yes, yes, they can. They can see all what the player decided, and even the current distribution the player is playing from. That is allowed for the adversary to do.
And so the loss can be then conditioned. Like, for
Yes,
example, if
loss can be
you, like,
conditioned.
invert
Yes.
their distribution.
Yeah.
How do we, like, you said that the setting is adversarial?
Yeah.
But we also define the losses explicitly here, so it doesn't seem like it's adversarial. Like, I guess I was.
Oh,
saying-
this is an example. This is an example.
Yeah.
This is not the general case. I didn't prove anything here.
In that case, why do we need to choose IT randomly?
Elijah wanted to do it, so I went with his suggestion.
Sure.
Don't have to. It's not. This algorithm is not going to work in general. Can you think of a setting where this algorithm is not going to work?
Well, yes, I just meant in this setting, it seems like you don't even need this algorithm.
I agree. You could just pick always the first expert. Yeah, Joshua?
So for the lower bound, would it not just be like something times root t again? Because if you could do better than root t, then that means that you could go back to the setting where you had more information and then also do better than root t again.
Oh, okay. This is an interesting point that Joshua is raising. Joshua is saying the following. Why are you laughing? This is a good point. Let me repeat the point. The point is the following. Suppose that I had an algorithm that is able to get better than root t regret for this problem called the multi-arm bandit. Then I could apply it to prediction from expert advice and get a better algorithm there, because this is strictly more difficult. There's nothing easier here. I could just ignore the information. Oh, you're giving me more information. Give me all that information. I'm throwing to the garbage, using all the information I need and playing. Yeah, this is a great point. So, yeah, Joshua's lower bound, this is correct. I love this lower bound because it involves thinking of what we have studied already in a very simplistic way, and there is nothing technical here, just understanding the concept. So this is a very good point. So Joshua says the following: the regret of any algorithm for multi-arm bandit is at least square root t log n. Because, did we talk about the square root t log n for multi-arm bandit? We gave an upper bound. I don't know if I gave you a lower bound, but I think it's in your homework. So, and if not, I'm telling you now, this is tight. Square root t log n is tight for multi-arm bandits. So you cannot hope to improve it. Do you all see the point made here? Very important point. Reduction, you should always use by reduction if you can. It's because it's easy. Good. So this is true. You cannot improve that. Can you give me something better with respect to n? Any idea? Yes.
Maybe this is very naive, but in a way, you could play every single action and count that as one single time step and then apply the prediction from expert advice, like the weighted majority algorithm.
No, this is a very good idea actually, but and we'll do something similar to it. But you're talking about an upper bound now.
Yeah.
I'm asking about the lower bound. Anyone can give me a better lower bound with respect to n? So I claim there is a lower bound of at least omega n. That's my claim. Can anyone prove it? Yeah.
Just do the same thing that Elijah was saying, but fix one person to have 0 loss.
Good.
You have to force to explore everything.
Good. Needle in a haystack. Okay. So let's say the losses are 1 everywhere except for one expert chosen at random, whom I give the loss of 0. Then clearly you have to explore every single expert, or at least half of them, to succeed with probability at least half, finding the needle in a haystack. Okay. This is a lower bound for array complexity, classical lower bound. Everyone with me? Okay, so this shows you already that this is a harder problem, strictly harder than prediction from expert advice. Because here we have log n and here I need n. So what I want to do now is design an algorithm for multi-arm bandits. By the way, historically, does anyone know where the name comes from, multi-arm bandit?
Is it casino?
Yeah, that's right. So the idea is that in the casino there is this slot machines, and each one of them is a random or maybe biased towards the house usually, and then you can think of a setting where one of them is favorable, and you're trying to find it and kind of gain as much as you can. So that's where the name arises. I don't think it's a very good name because they're all rigged against you. So now my question is, how can we design an algorithm for this problem, an upper bound, something that has a good regret bound, in this very challenging setting that's even harder than what we discussed so far? Any idea? You had a good idea. What was your idea?
Just iterate through all the actions and count that as one step for expert advice. So you have an array of losses, basically, and then use the weighted majority algorithm.
Okay, that's not a bad idea. So Edward's idea is to, I only get one bit of information, but let me go over all possible actions. In what order? Arbitrary order.
Yeah.
So let's say 1, 2, 3, up to all of them. Then I kind of gather the information from all arms and count that as one iteration for another algorithm. So it's a very good start. It's a very good start. But here's the issue. If I have a prefixed order, then what could happen is that I will lose because the adversary will know, oh, he's going to iterate 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, I'm going to give him a loss of 1, but the rest are going to be all 0. And that kind of will ensure that I have linear regret. Yes, Alex?
I just had an idea, I guess, but
Yeah, go shoot.
like maybe something kind of like Hatch, I guess, but you only update the weight of the like bandit that you selected.
Okay, that's a very good idea. This, what you describe now is called XP3. It's a sophisticated algorithm to analyze. So I will describe it, but I would say this is a harder algorithm than what I'm looking for. I'm looking for something easier. Jerry?
So the same idea, but if you randomize the order, is it equivalent to a prediction from expert advice, but like you have over n effective time steps, like t over n?
So the suggestion is to use Edward's idea, then randomize the ordering, and then proceed with according to some other algorithm. So here is the issue with this, the problem with this algorithm that you're suggesting, which is it's good in one regard, that you will at least have randomization in the beginning, you'll get the average reward in particular n tuple of actions you're doing, but then you're doing another n tuple, and you're basically, how many times are you playing each expert? The same exact number of times. So that has to change, right? If there is one expert which is the best, we need to converge to it. Yes, Ben?
Maybe sometimes you explore randomly.
Yeah.
And then other times you plan as best.
Okay, good. So that's where we're heading. The idea of a random permutation over the actions, that's good for exploration, for just figuring out the space. And indeed, there is something called the exploration
To
exploitation.
effectively explore an action space using permutations,
Why
you
is it saying
should
that?
employ Thompson-Sandlin Boltzmann exploration.
I didn't say okay, Google. So there is something called exploration exploitation. Paradigm. And this is what this refers to is the inherent challenge in gathering information and making use of that information. So when you talked about both Edward and Jerry, you talked about choosing a random permutation. That's very good for exploration. You can explore the space by that. That's what you wanted to do. You wanted to see how much is every expert worth. But then let's say you found out, okay, expert number 1 is much better. You need to exploit that somehow. And how can we exploit that? So I think in the very beginning comment you made, so how about we use some other algorithm that we already know? Because once we have the information, we already know what to do with full information. We spent 6 lectures already. I hope you know what to do, right? So we can do gradient descent, we can do multiplicative weights, we can do all sorts of things. So the first algorithm that I'm going to describe is called simple multi-arm bandit, simple MUB. It's a very simple algorithm, and it separates out exploration and exploitation. And the way it does it is the following. So we're given an algorithm A for prediction from expert advice. This algorithm knows what to do for prediction from expert advice. It can be, for example, hedge or all-on gradient descent. All-on gradient descent also works for prediction from expert advice, as we've discussed, because the decision set is going to be the simplex. Then what we're going to do for t equals 1, 2, and so on, I'm going to let bt be a random variable, which is going to be 1 with probability delta. And on this delta probability, I'm going to tune delta later, I'm going to explore, I'm going to gather information. So if it's 1, then I'm going to pick it uniformly at random from n. Then I'm going to create LT hat, a random vector. I'm going to create a random vector in R to the n in the following way. So LT hat of I is going to be LTI if I equals IT and 0 otherwise, multiplied by n over delta. And then I'm going to update xt plus 1. The distribution that I play is going to be the algorithm on the LT hat 1 up to LT hat t. So I'm updating my distribution according to the vector that I have created. And I will show in a minute this vector is a good vector. It's the expectation of LT hat is going to be LT. It says if I have the entire information, because I have the entire information, I can use whatever algorithm that I use. And otherwise, so BT0, I play XT, I don't update, and I take LT hat to be 0. So I don't update at all. And xt plus 1 is xt. I don't change. So it is important to me that you see this algorithm, which is actually a reduction. It's not fully specified. The reason it's not fully specified because it depends what kind of algorithm I gave it. If I gave it multiplicative weight, it's going to do some multiplicative weight update. And if I give it gradient descent, it's going to do some gradient descent update. On purpose, I'm describing it this way. This is good for your thought process. I can reduce one to another. And in fact, I'm very happy Edward at least got what I said so far in the 6 lectures we had and said it by reduction, right? You're saying I used some other algorithm. That was good. I like that. Is it clear? The algorithm is clear? Yes? Why are you sitting so far away? You're always sitting here. what can't you read?
The two different cases for the LT hot I.
Oh, here.
Yeah.
You know, it's not my fault that the board is very dirty already. Let me write it here again. So this is going to be LTI if this is the I that was chosen. So IT equals I. IT is the point that I play, and 0 otherwise. And all of this is multiplied by n over delta. pick. Yes? Sorry?
Why n over delta?
Y n over delta, who can tell me? Joshua, you can tell me, yeah? Don't be afraid.
Because you only selected every every delta times.
Yes, correct. Correct. So, I need
so
the,
like in expectation.
exactly right. So let's look at the expectation of LT hat. And that's equal to what? With probability 1 minus delta, it's 0. And probability delta, it's equal to n over delta. And then it's all going to equal to these two cases here. I can actually look at every case here. I. So either it's LTI or 0, and this happens with probability 1 over n. This happens, doesn't matter when this happens. So all of this is equal to LTI. So the expectation of LT hat I is LTI for every single coordinate. I went over it very quickly, but I hope this is not a hard calculation. I hope it's clear to everyone. Let me also say the following. LT hat T, Euclidean norm, is bounded by what? Jerry?
N over delta.
Yeah, correct. Why?
At most one place.
Correct. So I assume the losses are between 0 and 1. This is most n over delta because I scale by n over delta. And same goes for the absolute value of every coordinate. Of course, it's also bounded by n over delta. So the infinity norm, the L2 norm, all norms are bounded by n over delta. So here is the theorem I want to prove. If A is online gradient descent that we studied in lecture number 3, I believe. Then the grid of simple multi-arm bandit is bounded by t to the 2/3 n to the 1/3. No, but also n to the 2/3. And this is not yet, one second, this is not yet maybe the optimal bound you can hope for, but at least the algorithm is very easy and very simple to describe. And the regret is sublinearity, so on average converges to 0. And if you compute how many iterations do you need this average regret to be less than epsilon, you'll get something like n over epsilon cube or similar formula. So it does depend well on the number of experts, and it vanishes with t. The average regret vanishes with t. Yeah, question?
Wait, is this independent of delta or choosing an appropriate delta?
For an appropriate delta. And I believe, let's write down what delta is. I'll compute it in the proof. I don't see it right now, but this will be easy to compute. Yeah.
I thought we said earlier that the lower bound was 10.
Yeah.
So it's like n
Well, this is, so n is a lower bound on how many iterations before the regret starts vanishing. So to get regret less than epsilon, on average, you need at least n iterations. This does not contradict that. If you compute how much this to be, if we make the calculation, this expression less than epsilon, and extract t, t will be bigger than n. It will be n over epsilon cube, I believe. Okay? Yes.
So when VT is 1, then we select some random index from the n tuple, then why is there further randomness into what we play? Like, if we select IT, then why don't we just play IT every time?
There are two separate randomnesses here. One of them is which iterations would perform exploration. That happens with probability delta.
Right.
And then there is another randomness. Okay, we decided to explore. If I explore, I can't always pick the first expert. I need to decide which expert to pick. So that's the second randomness of choosing one out of n at random.
But once we pick that expert, then we would play that expert only. We would choose that expert in that iteration, right?
Yeah.
Then like LT hat of I should always be, I mean, it should just be LT of IT, right?
If I is equal to IT. There are n coordinates of LT. LT is a vector, it's not a number. LT is a vector in R to the n. It's not a single number. LT IT is a number, and LT is a vector. Yes?
I'm struggling to understand what happens in the case in which BT is equal to 0.
Basically, nothing happens. I don't change the algorithm, I don't change anything, and I don't do anything.
Then why do we couldn't?
Well, I need to say what will happen. Let's say it turned out to be 0. I can't just say give up. I need to say
Or
you
can
have to
we
do
just
something.
make delta 1 and always have?
No, the regret is not going to work. You will see that. It's an interesting thing. It's an interesting point. But you will see in the analysis it's not going to work. Yeah?
So for the round where BT is 0, you don't update anything.
No.
I was like wondering, isn't it wasteful to throw out that information?
Very, very wasteful. Very wasteful. It's not going to be an optimal bound. It can be improved.
Okay.
Because right now what I'm doing is I'm separating exploration and exploitation. This BT variable says if BT is 1, I explore. And if BT is 0, I exploit. Later I'm going to merge these two things, something similar to what Alex was saying before. Elijah, you had a question?
Did you say that you can assume that the losses are
I'm going to forbid you from sitting here. This looks too comfortable for me. Yeah. Sorry, did I say?
I asked if you said that the losses you can assume are bounded between 0 and 1.
Yeah.
Why is that a okay assumption to make?
Do you have a setting where the losses are not bounded?
Well, I guess you have stated that like this property about the norms, which I assume are going to come in. So
Oh, of course. Look,
if it's
some
not-
bound we will need. Now, the world is bounded, okay? Or I'm not saying the universe. I think even the universe is bounded, right? This is what physics. Anyone physics major here? No physics major? How can I not have any physics? Yeah, physics major? It's expanding, but it's bounded. Otherwise, there would be nothing to expand. If it's unbounded, there would be nothing to expand. So by the very fact it's growing, it's finite. But never mind the whole universe. So whatever problems we're trying to solve here on Earth, they're all bounded. So I think it's a fine assumption. It's just a matter, the bound can be very large, and we want to be able to make sure that we scale well with respect to that bound. Now, regret is a scale variant quantity, as I've emphasized before. If I scale up all the losses by factor 10, regret is going to go up by factor 10. That makes a lot of sense. So therefore, I'm assuming it's between 0 and 1. If they're between 0 and 1,000, scale by 1 over 1,000, and then continue. And later we scale the bound by 1,000.
The homework also shows that it's fine.
I think there is something like that.
Yeah.
Yeah. Thank you. Yes, Colin?
You said it was wasteful to have like this BT equals 0. So is there like an optimal choice of delta? Would that optimal choice be 1 then for this theorem?
Optimal choice of delta?
Yeah.
Absolutely, yeah. I just said I'm going to compute it later because I forget how things work. So once I start the math, it will come out. Yeah. Any other questions? So my regret, let's prove the theorem. And first I want to prove a lemma. So xt is my distribution at time t, lt is the real loss vector, lt hat is the imagined or created loss vector, it is what I actually played. So my claim is that the expectation of lt it is less than the expectation of lt hat xt, transpose xt, plus delta for every t. That's the claim. It looks like a technical claim. It is a technical claim. What it's saying the following. It's saying that the loss I suffer, I can relate it on expectation. The expectation here is over which randomness?
The expert.
Correct. Expert I choose. That's the only randomness here. And by the way, all expectations here, if you are a fan of probability, there is no martingale here. It's all conditional expectations given the entire history so far. So I'm filtrating on the entire history. Independent of whatever happened so far, this is true. Because I choose fresh randomness. I don't depend on what happened so far. So expectation LTIT, expectation over IT here, is less than expectation LT hat XT. What is the expectation over here? What? LT hat, yeah, LT hat. This is the creation of the LT hat. There is a bit more subtlety here because XT himself is also depends on the history, it was random and so on. I'm ignoring that. I'm filtrating on the entire history. So conditional on the entire history. For any XT, is it true? For any XT. Here I created this LT hat plus delta. So this is the claim. And let's prove this claim. So I'm going to separate out, but I should say, why am I doing that? So I want to bound, this is my actual loss. I want to compare this to the best in hindsight. For that, I don't know what to say about IT, but I do know what to say about the XTs. XTs come from the real algorithm. There was a real algorithm going in there that was actually played, and that has a regret bound. Every time I updated it, the vectors, and so on and so on. So this I will be able to say something about. This I can't really say anything about. That's why I'm relating the two quantities. So let's look at the expectation of LTIT. And this is the expectation of, so probability BT equals 1. Expectation LTIT BT is 1 plus probability 0, expectation LTIT BT 0. So this, I don't want to say anything about it, because I'm not creating any new, at this point, this is a hard thing to argue about. So I'm going to say this is bounded by delta. It happens with probability at most delta. And here I have 1 minus delta times this expectation here. I'm using here the fact that the losses are at most 1, otherwise this would not be true. So now I claim this is equal to, or less than equal to, delta, plus what I have here is expectation of LT hat XT, given BT is 0. The reason is that IT is, how do you denote independent? Is there a notation for that? I forget. Well, okay, yeah. is independent of
One
xt.
more vertical line.
Like this?
Two vertical lines.
Oh, two vertical lines. Okay, thank you. Yeah. Okay. IT is independent of xt given that the bt is 0. So this LT hat was independently constructed of the xt. Pick IT at random and constructed. And this is at most delta plus, I can remove the expectation. And the reason I can remove the expectation is because these are all non-negative random variables. All the numbers here are between 0 and 1. There is nothing negative here. So maybe there is more mass coming in from other places. I'm fine with that. It might look easy, but if you reason about this is a very subtle thing to kind of work out, and I encourage you later to go over it step by step, and I guarantee you, you will be confused at some point about something that's happening here, but this is correct. So let's use this lemma. But the lemma relates the two quantities that I discussed, the actual loss I suffer, and the loss of the algorithm at time t over the L hats. So let's now look at the expected regret. Which is summation over t, expectation, into IT minus IT I star. Now I claim this is less than delta t plus summation over t expectation L hat xt minus L hat x star. Or if you want, it can be I star or x star. And here I'm using the lemma. And I'm also using the fact that the x star is independent of the hats. That depends on the L's. Yes, it does depend on the L, but it doesn't depend on the L hats. Okay, so the L hats I created myself out of my own volition by choosing random stuff and defining these random vectors, but they have nothing to do with the I hat, x, with the x star. Yeah?
So I could not get why, like, given BT 0, L hat becomes like the last step.
This is hat. So, this hat.
So then why is it independent? Like, why does BT equal 0 get removed away?
As I said before, this is part of the probability space. So the expectation of LTXT has two parts. BT is 0, BT is 1. BT is 1 only adds more. It's only bigger because these are non-negative random variables. Everything here is non-negative. Okay? So conditioning, if I take a random variable condition on something, rather than not conditioning on it, only be big. These are non-negative numbers. So now, and I remove the, or I should say, it's fine for now. So let me continue. I was here. So this is where I go to. Now I want to argue about what's written here. What is written here? Yeah.
Like the expected regret of the actual.
Very good. Expected regret of the algorithm A, right? Over which iterations? This only happened when the BT was 1. That's the only situation where my algorithm gets updated. Okay? So, what I get here is the following. This is less than delta t plus regret of the algorithm A over these L hats. L hats 1 up to L hat t. This is over bt equals 1. Otherwise, there is no meaning to that particular. LT hat is 0, there is no loss there, there's no best in hindsight, there is nothing there. Now, what is the regret of on-and gradient descent over t iterations? That already we studied. This is GD root t, right? So this is delta t plus GD square root delta t, because this happens, it's expected regret, and the number of iterations here is delta t. And the gradient bound, we calculated already, to be n over delta. The diameter of the simplex is what? Square root 2, yeah. So this is delta t plus what I have here is n, and then square root t, 2t over delta. Now we can compute the delta. So let's equate these two terms. So delta t equals square root n square root t over delta. So this means delta to the 3 over 2 equals n 1 over root t. And this means delta needs to be n to the 2/3 t to the negative 1/3. I think if my calculation is correct. So if I plug that in, I get n t to the 2/3 n t to the 1/2 times negative whatever. So you calculate this 1 over. So t to the 1/2 plus 1/3, this becomes something like that. Am I right here? Oh yeah, this is all square root. So this is, again, t to the 2/3. So all of this is O of n to the 2/3, t to the 2/3. You can check my calculation. I think it's correct. Yeah, Colin?
Why is G equal to over delta?
We calculated it here. So look at the gradient. Okay, what are the losses? What are the loss functions? We're applying on-and gradient descent. Good, important question. We're applying on-and gradient descent over a sequence of linear loss functions. So what are we're applying on-and convex optimization, right? Ft of x is equal to Lt transpose x. These are the functions I'm using. The gradient is Lt. So do you see that the Lt norm I computed here is at most m over delta? That's a good question. Yeah?
Do you think there's a way to use adaptive delta to make the loss different?
No, I don't. The reason is, the question, let me say, this is an important question. So Angelos' question is, can I adapt delta on the fly to improve the bound? And I believe the answer is no. And this is inherent to the fact that when I choose to explore, I choose uniformly at random. I'm not using my knowledge of how good the relative experts are in my exploration. Anand, I forgot to pass the attendance. Can you pass the attendance sheet? Thank you. Okay?
But does it make sense like to want to explore more in the beginning and to explore more in the end? So maybe you would think, but maybe it's not that much better.
It's an adversarial setting, right? So maybe in the beginning it's all the same, then in the end it starts becoming complicated. I think this is inherent to the separation of exploration and exploitation. So every time I explore, I basically lose constant. Every single time I explore, I lose constant. Now the amount of exploration then has to be at least some quantity, and this quantity has to be at least, behaves like square of t for optimal rates. So you will see, in this trade-off, it comes to be t to the 2/3. Or 1/3, yeah, t to the 2/3. Because it comes in a hard way. It kind of, every time I explore, I lose a lot. Maybe I discover that the best exploit is 1. It's really by far much, much better. So when I explore, what would I do? I will not give uniform distribution to everything. I'll do something a bit more intelligent. Yeah.
But as you're observing the actions that observing the logic, and you will start to build a
Yes. Yes, exactly. So let's think. You guys are all moving ahead to the next. I think I can use this nice clean board. Let me see if I don't have to. Yeah. I'm going to take a gamble and try to use the clean board. So, question: can we improve upon this bound? And the answer is yes. So, it is possible to obtain a better bound. And how do we do it? We need to move beyond uniform exploration. Does this make sense? So, I guess, Alex, you had a good intuition before how the algorithm looked like. So what would you do?
Well, I guess what I was saying before is like kind of a similar thing to the hedge algorithm, but we just whichever one like we randomly select, then we just update the weight of that and leave the other weights constant or the same as they were in the previous version.
Okay, and how do we explore the next iteration? Saying always choose an action according to hedge. Randomly.
Yeah, well, I guess it would still kind of make sense, right? Because like, when you update the weight, it's gonna, or like when some action incurs a loss, that's gonna decrease the weight of that. So if you like pick one thing too many times, then it's gonna already get incentivized to pick it.
I agree. I agree to Alex's suggestion. So the variant of hedge that I can apply, I guess what Alex is saying is the following. I just play hedge. I play hedge, which means I have distribution over the different experts. Then every time I play them, I say loss. Fine, let's update the weight of that loss. I don't know what the other weights are, but who cares? I'm going to assume it's 0. I'm not going to update them. And that's all I'm going to do, this hedge. So this algorithm is called the XP3. It's a very nice and elegant algorithm. And let me spit it out. So initially, I take x1 to be 1 over n times the uniform vector. I start with the uniform distribution. And then for t equals 1, 2, I do the following. So I play it chosen from xt. This is the difference from the previous algorithm where I played uniformly at random. Now I don't play uniformly at random anymore. I choose according to the distribution xt. Define L hat t at coordinate I. So this has to be a bit different now because I'm playing according to a bias distribution. This has to be LT of I divided by XT of I if I equals IT and 0 otherwise. So this is the random vector for the all losses of the entire set of experts. And what do I do now? I update, as usual, update the hedge update. So yt plus 1i is xti times e to the minus epsilon lt hat I. And then renormalize. So xt plus 1 is yt plus 1 divided by the L1 norm of yt plus 1. So this is exactly the same as hedge, except for this stage here. This is a different stage, different from what we had for hedge. For hedge, we knew all the LTs and we just did this update. Now we don't know what it is, so we say they're 0. 0 means basically no update here. E to the 0 is 1. So there is no update on those expressions we didn't play. So this is what I want you to pay attention to. This is a very non-trivial thing to do. I mean, it was intuitive, I guess, for you, but it's non-trivial because what can happen is you might get locked in to some expert. It's so good, you never ever explore the other. There is an exponential updates, right? So some experts got a low loss, they get diminished, and you always keep playing one expert, and maybe the situation changes and some other experts become good. So it seems counterintuitive maybe in some way, and yet the following theorem can be proven. This is by Auer, Chezabianchi, Freund, Shapiri. So they said, they proved that the regret of exp3 is bounded by square root t n log n. So this is very, very similar to the regret of hedge, but we have an additional n here, which you would expect to be unavoidable according to what we discussed. Yeah?
So are we also assuming that the losses are up to 1?
Yeah, same setting exactly. Same setting exactly. So losses are up to 1. The epsilon needs to be tuned according to, there is some epsilon here, so with epsilon being 1 over root t times something. So there is a tuning that happens here, and if the losses are between 1 and 1,000, then the tuning needs to take that into account, and the regret will depend on 1,000, just like the other algorithms. So basically, it's easy to prove that the regret over the L hats is what we want, but here's the issue. The expectation of the L hats is what? Expectation over the choice of IT. Yeah. It's LT, it's unbiased. Nevertheless, the magnitude of it can be very large. It's no longer bounded by 1 over n. It depends on the probability that I choose from. Okay? What I can bound is the variance of LT times XT, LT hats times XT. And that is a magical property that comes into here and allows to prove this theorem, which I'm not going to do on the board. It's very similar to hedge, but I encourage you to read this in the book. This is an interesting technical point. Very interesting technical analysis. Yeah?
Why did we, for updating XT this one, why did we use the L1 norm?
You want to normalize it so that they all sum up to 1. So L1 norm is the sum of all the, I could have written here the sum of coordinates. They're all non-negative. It's more succinct for me to write the L1 norm. Questions? So you could have asked me, is this tight? Is this the best you can do? And the answer is no. This log n here can be removed. It's possible to even improve it to this. That's really not a significant change, but it's possible to do. And this is tight. This is the best you can hope for, asymptotically, by a very similar algorithm to hedge. And then I can ask, okay, this is lovely, great. Now I want to apply it to routing. And you remember routing, that motivated our move from prediction from expert advice to online convex optimization a few lectures ago. Because we'd like to deal with structured decision sets or portfolio selection, or something more sophisticated than just an expert. when the number of exploits becomes very large, becomes exponentially large in the natural characterization of the set. There are two problems that come into effect here. Now, two problems. Not only computationally is it problematic to run XP3 or simple MAB. There is also a problem of regret, because the N now comes into the regret, not only into the computation, it comes into the regret. Previously I had log N, square root T log N. Even if N is exponential, it's in the log, not the end of the world. So now, this is something I want to stress. So if I want to online route, there is exponential in computation and regret. So, which makes sense, it's a harder problem. I have a double trouble over here that exponential terms will make their way both into the feasibility of implementing my algorithm in feasible time and in the statistical or regret bounds that I want to obtain. Everyone with me? So that's a huge problem. And what I'm going to show you Thursday is how to overcome this problem. It's going to be a magical, magical lecture, and I really hope you should try to make it. It's going to be a beautiful lecture on Thursday.